Swayam Prabha. Digital India. Educated India.
Good morning, students. So let's get back to another very important topic in the dynamics, which is impulse momentum equations. This is the very basic dynamic equations only, and which are slightly modified so that they can address some other important problems. So basically, we have this dynamic equations. So the basic equations are, we start off with only basic equations. So this we have been doing it for 2D. So this is the basic equation. So the unbalanced forces obviously is going to create motion of the body, which we represent as the mass times, accelerations and mass times accelerations here. And so let's acceleration and angular acceleration. So this is going to result into this one. So this is the basic equation. So these are the actual forces, and this is the effective forces, we call it. So that means the effect of this one. And then these are equivalent, and whatever you do on the left side, you can do on the right side as far as equations are concerned. Okay, so this is the basic Newton's laws, you can say that. And then what we would like to do is that we would like to do a little bit of integration. So the basic equation can be written as okay, IG, or sometimes we call it as I bar, both mean the same. So these are the two equations. So what we would like to do is that we would like to integrate it. So we take the basic equations and then we would be integrating with time. So in time means what will happen over an interval of time. So this is the instantaneous depiction of the dynamic equilibrium, and then if there is over a time interval, you would like to see the changes. So for that, what we would like to do is that we would like to integrate it integrating with time on both sides. So what we have is that Fi T, T1 to T2 on the left side, and then this is equal to so well, you have done this earlier to some extent. So acceleration, if you write it as dvg by dt and dt here over 1 to t1 to t2 will become one to 2. So I'm just writing 1 to 2 because the integration variable has changed to dvg, and then this we call as mvg2 minus mvg. Okay, so this is a very simple integration of the basic equation. Okay, so this is about the linear, the first equation, and then you can also say that this is on the right side. If you see, mass times velocity is also known as the linear momentum, and so the change in the linear momentum over time 1 to 2 is given by the integral of force over time from t1 to t2. Okay, so this is momentum equation. There you call it as a linear momentum. Okay, and then we can also do the same thing for the second equation. For the second equation of the motion, so we'll do the same thing. And ig times alpha times tt t1 to t2, which can be written as this is alpha, and which can also be written as d omega by dt dt here. Okay, just doing this d omega by dt and dt here, and so it just like whatever we have done earlier. So this will become ig times omega 2. Well, we will just one more step here. Okay, so this is just putting it, rewriting it again. Okay, so this is the another equation, just like your linear momentum equation. So this equation is, you can see that this is a version which we have simplified it from 3D to 2D, and so that is why it is just a scalar equation here. This is as far as the plane motion is concerned, as far as the 2D motion is concerned. So the rotation is about z-axis, and that's why it is just one equation. So this is angular momentum. Angular momentum equation. Okay, so this is one is linear momentum, the other one is the angular momentum equation from T1 to T2. So we can even write this one interestingly as, so this is and then this f dt is called the impulse, and on the right side it is linear momentum change, and so this is again impulse, angular impulse here. And so these things can be written as, let me write it here, same thing can be written as, what is that? We will rewrite it, change it as mvg1 t1 to t2. This is the first equation. And so similarly, okay, so these are the equations from state 1 time t1 to t2. So what this says is that the linear momentum at time t1 plus the impulse, what is happening over t1 to t2, is equal to mvg1. So this is the linear momentum after at time t2. So the same thing is true for angular momentum, and this is the impulse of the moment over t1 to t2, and then this is the angular momentum at time 2. Okay, so this is the same thing whatever you do. So these things can be depicted in a picture. So these two equations can be shown together as like this one. So we have, so this is linear momentum, I'm sorry, and this is the angular momentum. And to this, if we add to this, we are okay. So this is we are showing it in the form of picture. This is the both of them put together, just like we did it for the sake of forces and moments. So we are doing it for this impulse momentum equation. So why we show it in this manner? So this linear momentum is shown at G, acting at G of point G, that means the whole mass concentrated there. And so similarly here it is shown at G. So what essentially this means is that this is much more than a simple equations. It also says that you can equate the linear momentum, you can equate moment of this ig omega 1 about g and this mdt and about g, or we can even take some other point here, any other point here, a or something like that here, and you can take, you can also use moment of momentum is nothing but angular momentum about a also. Okay, so you can also use angular momentum about a equation. Okay, so this also can be done. So that is the beauty of showing it in the form of a figure, just like free body diagram. And So here we are showing the free body diagram. It's essentially a free body diagram. In fact, if you have connected bodies, you can even isolate the free body and you can apply this linear momentum equation. Okay, so now just for the sake of illustration, so let's take a very simple example. Is a ball is thrown on the ground with some velocity So what we mean by that is that we have here, the problem is that we have a disc or a cylinder with a velocity v here is thrown on the ground. Okay, this is just like your bowling game. So in the bowling game, so you just throw the ball on the ground with a certain velocity v naught. So you can very well see that at this moment when you throw it, so there is no rotation of this one. It's only a linear velocity this ball has, and then as it moves down the line here, as it moves down the line, so there is because of the friction contact here between ball and the ground, so it starts developing a certain amount of rotation, and after some time this is the steady state. So it starts moving omega prime. Okay, so after some travel here because of the friction and the ground, so some part of this linear velocity is converted to angular velocity. Okay, even for that matter, the energy also, the linear energy is converted to some kind of rotational energy also, and finally it reaches a steady state where it's a pure rolling. This is a pure rolling state, and then you can find out what will happen. In fact, this kind of problem also we have done in the case of direct dynamic equations. So that a cylinder with a rope wound around that, and then you pull it and so on. So there also this kind of, in fact, we considered various cases there, a pure rolling and sliding and so on. So similar thing. So whenever you have this cylinder, so a steady state or a pure rolling consists of this v prime and omega prime. They are related in a certain manner. Okay, so if r is the radius, so for pure rolling, so v prime is r omega prime. So okay, so we don't go into that. So in fact, for pure rolling, we say that this point here at the bottom will have a zero velocity with respect to the ground, whereas here this bottom point here is having a certain relative velocity v naught with respect to the ground. So that relative velocity will become zero in the case of pure rolling. Okay, so now, so to go from this to this, so that means that time 1 to 2, so a certain process has taken place, and during that, so certain impulses have been generated, and then so that impulses will change the linear momentum and angular momentum. So let us make the equation. So make the equation first in the graphical sense. Graphical equation. So we have okay. So we'll put here linear momentum, and we know that it's only horizontal and there's no other rotation here, and so this is all what you have here, right? So for that, this is state 1 T1, and here, so the forces that are acting is the weight, and then there is normal reaction, okay. But when we want to add this effect of this one to this linear momentum, so that's we have to integrate it. So this is W times T1 to T2 because of the weight, and this is NDT, and this is so all the impulses are now taken care of this one. T1 to T2. So everything is integrated here, all the forces, and there's no M or anything acting here. So these are all the forces. So this is T1 to T2 we have integrated, and so this is equal to so now the final linear momentum is mb prime, and this is what is the momentum here. So this is Ig omega prime. Okay. Okay, so this is the equation in the graphical form, and here there are so many variables here. There's n is, of course, you can make equations in the vertical direction, you can make equations in the horizontal direction, as well as you can take moment about any point and make the equation. So basically, if you want to make a linear momentum equation, so in the x direction, so it is mb naught plus, here the things are in the vertical direction, you have minus f dt, and this is equal to mb prime. Okay, so similarly in the y direction, there is no linear momentum but only ndt minus w dt. That's all. This is in the y direction. And the moment about g. So how much is the moment? So that's only, this is the center point, of course. So then this has f dt. So f dt has moment about g. So that's nothing but f dt multiplied by integrated times r. And there on the right side you have Ig times omega prime. Okay, so these are the three equations. And how many unknowns are there? So if you count unknowns v prime and omega prime, as well as n and f. Okay, so there seem to be more unknowns than the equations, right? What is the other equation which we can use? What is f? So the other equation, one more equation, is because of the interaction between the wheel and the ground. So during this process of T1 to T2, so there is a certain slip is taking place between these two, and so there is a friction, and that horizontal force is nothing but that friction force. Since it is a slipping, so F is equal to mu times N. So because of so the friction force on the ground due to slipping is nothing but F is equal to mu times N. So this is the constraint, okay, information between the slip between the ground and the disk. Okay, so you have enough equations, so you can really do it. Okay, so that's what you can, if you want to solve all forces and all that. But on the other hand, if you are not really interested in this calculating this f or something, so you can use these equations. For example, ftt, you can substitute it here. And how much is this ftt? So we can find out mb naught minus mb prime. This is 1, 2, 3, 4. So you can substitute 1 in 3 and you can directly solve for. So it is really, if you want to put it, take this and then put it here. So it is mb prime, no, mb naught minus mb prime. So that's times r is equal to Ig times omega. So which we can put it as v prime r. Okay, finally. So you can calculate the v prime here. Okay, you can calculate v prime here, and that is the answer. So you can do it, you can calculate, and okay, so that is a very simple calculation. Okay, so we have done 3 equations or 4 equations, and after that, if you want f, n is w, which you can see. If you want f, once you calculate n, so you can also calculate f. Is very simple here. And so all the unknowns are calculated. So instead of formulating all the 4 equations and then calculating these things, so you can also do a direct application of the moments about some other point here. So if you take this bottom point here, And instead of taking the moments about G, now you can take the moments about A. So what is the advantage of taking the moments about A? So then all these things are passing through A, and so these will not contribute anything to the moment. And so what you have here then as a shortcut, you can directly apply moment, angular momentum equation momentum balance about A. So what does that mean? So that means that so it's mv naught times R, okay, and that's all. So this is 0 here, and on the right side it is mv prime times R, because this mv prime has a moment about A together with, as such, the angular momentum. So angular momentum will not have any change because it's already an angular momentum, and either you can take it at G or you can take it at A, doesn't matter. Only thing is that there is an additional contribution of the moment of linear momentum of mv prime about R. So from this it's very easy to see mv prime R Ig times v prime R. Okay, so this is how we can calculate. So v prime can be taken out here. So from this you can calculate. This is mr squared depending upon your I. It may be a disk, it may be a ball. So depending upon it's a half mv square or 2/3 mr square. So you can calculate v prime. Okay, calculate. You can calculate v prime. Okay, so this is a very simple problem. So essentially we could even have done it by applying our first direct equation of forces and equation of moments. So you could have done the same thing. So there is not much difference. However, this is going to have certain other advantages as we go along. So one more thing here is that the same ball here can be the same thing here. Corollary of the same problem, you can throw the ball thrown on the ground, or a ball rotating at omega naught is placed on ground, and after some time, so what happens is that so here this is a thing which is placed on the ground. So then so just like we have said the same thing with a certain initial velocity. So now we have only an angular velocity omega naught, and we would like to see what happens. So as it placed on this one, then what happens is that because of the friction force here, okay, there will be a slip and there's a friction force here, and that will create a forward force here. Okay, so there will be a force in the forward direction, and finally what happens is that you will attain a V prime and a omega prime here, so which is again a steady state. So we can even directly show the graphical picture of this one. So what's the graphical picture? So there is a this is the picture. So this is the initial angular velocity disk width, and then this is forces acting, and this is not really, I mean, this is really a steady state. Okay, so this is between T1 to T2, and this is at T2. Okay, so if you want to actually make a graphical equation in the form of figure, so what we have here is that so it's rotating. So this is the initial state, right? Angular momentum. There is no other linear momentum. So what we have here is again, so we have a W here, so in fact earlier I put the force direction in this direction. Now I am putting force in this direction. So what is the difference? So earlier the whole ball is moving forward, and so then there will be, relative to the ground, this is moving like this, the ball is moving like this, so obviously the force will be acting in the opposite direction. Whereas here, if you look at the rotation of this one, so the ball is rotating in this direction, clockwise direction. So at this point it is moving, this point is moving to the left, and there will be a forward friction force. Okay, so what we have here, V prime so this is the final steady state. Of course, the steady state, as we said, there is a relationship between V prime okay, pure rolling. Okay, so this is just this same type of problem as we have done earlier, except that instead of linear momentum here to start with, now it has an angular momentum, and finally of course it is the steady state, and only thing here is that the force is acting in the forward direction. So you can see that because of this friction force which is acting in the forward direction, so interestingly it will give a linear velocity, a forward linear velocity to the thing. So you can see here that the equations are so the x equation is 0 to start with, and you have integral f dt, and this will give raised to mb prime. And in the vertical direction, so we have nothing here, and we have a very simple equation, and the moment equation here will be ig times omega naught, and here what will happen, this fdt is acting in the opposite direction, and this is equal to okay. So these are the three basic equations, and of course you can say that f is mu n, so that is also a constraint here, so we can use that. So this is the constraint equation. So constraint in the sense that the interaction between the ground and the cylinder is a generation of friction which is equal to mu n. So this is what, again, the same kind of equations or the rolling. Okay. So again, as I said, so if you want to simplify this one, an equation can be formulated a angular momentum conservation can be done for ma, so or otherwise we can directly take moments about yeah. So for doing that, so we have ig omega naught, and all others are 0 here, and here we have ig omega prime plus mb prime times r. Okay, so this is the equation directly, and v prime r so this is ig, you can take r here, and m square v prime. Okay, so you can find out v prime here. So that is the answer. So like that, so once you get experience, a lot of experience, so instead of writing all these four equations unnecessarily, so you can also, of course this is necessary, well, we don't use it, so we can use this one directly. Okay, so that is the application of impulse momentum equations for some cases. So the only thing again I'd like to point out, so in this impulse momentum equation, what we have done is that we have integrated the basic equations with time. So either you can calculate the ag prime and omega alpha prime, okay, and then you integrate it later, so that's also equally good enough. But however, this approach has certain very important applications which we are going to see in the next lecture. Okay, bye bye.